Okay, hello, good evening. Today we will present about the subject power system and system protection. We will focus to the transition stability test on IEEE 57 bus test system models, which we are using the EMTP software. Okay, this is our group members, which consists of 5 people. Student, firstly, me, Ahmad Hamzah bin Azman, Alexander Chon Jiachai, Liu Chiapin, TANWENKANG, and Nur Aidi binti Samuri. Okay, firstly, we go to for the introduction. We are given a project that we are required to by the power system planner to assess the rotor angles stability of each machine on the system. Okay, then we need to simulate the dynamic response of the system following a disturbance in the system. We proceed to simulate using the MATLAB R2013B software, which provided by the company. Then we build up the graph machines, rotor angle, machine motor speed, and generators and electrical powers at these times. Okay, this is the 4 phases which we use to simulate from the stables, and then for the marginally stables, then marginally unstables and unstable states conditions. So this is the objective for our project, which is the main aim for this project is to work on the IEEE 57 bus system using MATLAB software provided. And then the objective, firstly, want to simulate the dynamic response on the system following a disturbance in the system walk-on. Secondly, we want to assess the rotor angle stability of the given system for different types of disturbance. Next, we proceed to analyze the power system faults based on balanced and unbalanced faults techniques. Then, we want to determine the protection schemes which is suitable with the power system provided. Next, I pass to Nur Aidi to continue with the methodology.
Okay, good evening, I am Aidi. I will explain about the methodology for this project. For the methodology part, we use the Newton-Raphson method. The Newton-Raphson method is widely used for solving non-linear equation. It transforms the original non-linear problem into a sequence of linear problems whose solution approach the solutions of the original problem. The method is a powerful method of solving non-linear algebraic equations. The fundamental Newton-Raphson expression allow for convergence to be assessed by comparing power mismatch against a pre-specified tolerance rather than voltage comparison. Figure 2.1 shows the flowchart of Newton-Raphson method used to analyze the power flow of IEEE 57 bus data analysis system. So for the flowchart, the input is to read the system data and specified load and read voltage specification and regulated bus. Then from system admittance, then initialize for voltage and angle. Next is to update voltage and angles. Then decision to which specified condition satisfied. If no, we will go back to the update voltage and angle, and if yes, it will go to the output bus bar voltage generation. Next is the single line diagram of IEEE 57 bus system. For this single line diagram, we use 7 generators and 57 bus systems. Next, I will pass it to Alex.
Okay. Thank you, Annie. Now, next, I'll be talking about the rotor angles for examples 11.7. Now, as you can see here, this is the rotor angle during stable condition. As looking at the graph, you can see all of them are relatively stable, and thus is called in the stable condition. Next. Now, this is the rotor angle during a marginally stable condition. As you see, the amplitude is not really in sync with one another. They are quite different, but from afar it looks almost stable, so that's why it's in a marginally stable condition. Thank you. Next. This is where it gets a little bit interesting. This is when it's in a marginally unstable condition. As you can see from the graph here, initially it's okay, but then the bandwidth starts to get wider and wider, and towards the end of the test sample, or in this case 10 seconds, after the 9 second mark, it will tend to shoot up without bound. So there's no limit, just continues up because it has already exceeded the critical clearing time. Next. Now, this graph depicts the rotor angle during, as you can see, this graph depicts the rotor angles during a totally unstable condition, meaning it's totally up. As you can see, all the rotor angles they go their own way. So in this situation, this is called unstable condition. Thank you. Now I'm going to let the next presenter, Mr. Liu Xiaoping, to present.
Good evening. So I will present about this graph. As you can see from this graph, basically we get by adjusting the near end and far end fault clearing time to 1.01 seconds and 1.02 seconds respectively. As you can see from the graph, the motor rotor angle increased during 1 second because the fault is set at 1 second. Besides that, you can see that the angle of the machine's rotor remains almost at the same slot throughout the simulation. This can indicate that this is in the stable conditions since the slot is almost constant. So this is basically the speed during the stable conditions. And let's move on to the next graph. So basically, this is the generated electrical power during the stable conditions. As you can see from the graph as well, the slope is almost at the same constant, so there is no overshoot or anything in the graph. So it can be concluded that in this graph is operate in normal conditions. Okay. So this one is for the machines operate during the marginal stable conditions. As you can see from this graph, the slope is increased gradually, but then as you can see through the end, it decreases, become a smaller slope. Since it reduced to become a smaller slope, which means the system will become stable again. So although it started to become bigger at first, which indicates that there is fault, but it managed to go back to the smaller slope. So it indicates that this system is operate, which is before the fault clearing time. So which means that this system is operate in marginally stable conditions. So next we will go to see the rotor speed during the marginally stable conditions. So basically this is the graph, and then let's move on to the next graph, which is the generator electrical power during the marginally stable conditions. So basically this is how it's going to look like. So I will pass to my friend TANWENKANG to present the next two phases.
So for my part, we will present for the part of marginally unstable. Next slide, please. Yeah, this is the part for marginally unstable. As you can see, the line here, at that point slope up, and it notes that it is a marginally unstable condition. Next, please. For the machine motor speed during the marginally unstable condition, as you can see, it is obvious that the machine motor speed in the marginally unstable condition, and the speed of machine motor fluctuates while one of the speed of the machine motors increase gradually. Hence, it can indicate that the system is operated under marginally unstable condition. So, next. For the generated electrical power during marginally unstable condition, we can see that the rotors will accelerate differently when there is a fault, which means this is the unstable in marginally. Next. And finally, to the last stage, which is unstable condition. It is obviously to be seen that this machine's rotor angle is in unstable condition. We have no fluctuation at all. Next slide, please. You can see also in the machine's rotor speed, it is obvious also for you to identify it as unstable condition. Next. And the last graph for the simulation, which is the generated electrical powers during unstable condition. As we can see here, actually they are quite unstable, in a quite unstable condition. Yeah. Conclusion, I will pass to Hamza.
Okay, and then I will continue. For this project, we have conducted the power flow analysis in EMTP, which is electromagnetic tensor programs. We find that NIE 57 bus test system, its standard data is selected for this purpose. And the main objective in this project is to work on the 57 bus system using MATLAB software. Thus, we have simulated all the what we need to do. This is the dynamic response on the system following a disturbance in the 57 bus test system. And then the rotor angle stability of the 57 bus test system has been assessed for different types of disturbance, which is stable, marginally stable, marginally unstable, and unstable conditions. Besides from the traction stability test, we found that the power system fault have also been analyzed based on balanced and unbalanced fault techniques. And lastly, we can conclude that the protection schemes that is suitable with power system have been determined. That's all. Thank you.